quickly recapping what we did in the previous class. We basically introduced rate of progress of reaction. Okay. We considered three, or I just inform you that over the course of this course, we'll look at three cases in which the rate of progress of the reaction will be used. One is where you use the constitutive relation. For various purposes, that might be for analysis, for design of reactors, or for anything else. So, this is where you plug in the values of temperature and partial pressures, or temperature and concentration, and compute the value of reaction rate. You multiply it with stoichiometric coefficient to get the rate of formation of any species. You plug it into an appropriate equation in order to either do design or analysis or simulate the system, or whatever might be the thing that you want to do with it. Okay. The other case is that given experimental data, okay, can you get the rate parameters? Okay. This will also, in more advanced cases, also involve design of experiments. Okay. And then final thing is, given the data and given the reaction, can you get the mechanism? So, rate and how it is related to the mechanism. Okay. Rate basically means if you are looking at A disappearing or P forming, if you are looking at, for example, alcohol disappearing and ester being formed, rate basically tells you how quickly alcohol disappears or how quickly ester forms because of reaction. Mechanism tells you how exactly or what exactly are the various steps involved in that transformation. Okay. So, for example, if it is an esterification, you basically have an acid. From that acid, you need hydrogen to get extracted, or OH to get extracted, whatever the case may be. From the alcohol, you might have the H or the OH getting extracted, and then you have those two species come in together and to form the ester. There would also be side reactions which will result in formation of side products, byproducts, or whatever else might be, and your mechanism then consists of all of this put together. Okay. How is the rate of reaction connected to the mechanism and so on, that goes into the analysis of the overall system, and that is an important aspect of what we do as both chemists and chemical engineers, or for that matter even mechanical aerospace engineers are interested in that. Okay. So, this is really what we covered. So, the most important things that we covered in the previous lecture. We did talk about the Arrhenius rate law, and the Arrhenius form is A naught okay, and if there are multiple reactions, this is the form that we would have. Okay. And just a quick thing, Boltzmann's constant is nothing but R divided by Avogadro number. Okay. So, Boltzmann's constant is R in terms of per molecule basis rather than per mole basis. Okay. So, let us look at some reactions. Over to you. How will you write reaction rates for, or what type of reaction rates have you encountered? Let's look at the irreversible reaction first. K, Ca, Cb, right? That would be first order in Ca, first order in Cb. What else? Power law. What else? Okay. Other forms would be either the Langmuir-Hinshelwood type if it is a solid catalyzed, okay, or if it is you know, gas phase system with involves free radical mechanism, then it might also have complex dependence. If it is enzymatic, we talked about Michaelis-Menten. Okay, so okay. What if it's a reversible reaction? How will I write this? Yeah, forward minus backward. Okay. So, if the forward was, so what is most commonly you have seen? Yeah, right. So, this you can write it as Kf Ca to the A right. What is this fellow called? Hmm? Equilibrium constant? Inverse of the equilibrium constant, right. So, this is Kc. Okay. Sometimes in some books this term might be referred to as Q, or sometimes 1 minus the product divided by Kc might be referred to as Q. Okay. The term okay, how far it is from 1 determines how far you are away from equilibrium. Okay. If this is equal to 1, you are at equilibrium. This is just a mathematical representation of something that several of you already know. Okay. This particular part comes from overall thermodynamics. Okay. And this K equilibrium, not Kc, but K equilibrium is related to the free energy of reaction, delta G of reaction. Okay. We will come back to this in a bit. I will copy this slide later and we will come back to this in a bit. Okay. So, now let us get to what is an elementary reaction. Okay. If you look at the rate expressions on in the red color font, which one is an example, could be an elementary reaction? Okay. We will call this A, B, C, D. Okay. A, how many say A is elementary? No one? 1. After this 1, then there will be 20 others. B, several. C, okay, you have changed your mind. C, no one. D, no one. Yeah, yes. So, this time we will go with majority. The correct answer is A. This is an element. This may be, can be an elementary reaction. Okay. Others are definitely not elementary reactions. Okay. If a reaction is elementary, then in the power law, what the powers that the concentration or partial pressures are raised to will be equal to the stoichiometric coefficient. Okay. If they are not equal, the reaction is definitely not elementary. If they are equal, it is possible that the reaction is not elementary. It so happens that the power law kinetics, the powers are approximately the stoichiometric coefficient. Okay. So, Ca to the power A, Cb to the power B does not necessarily mean that it is elementary. It can be elementary, it may not be elementary in some other cases. Okay. But A, C and D are definitely not elementary. Okay. So, some examples of elementary reaction, I do not know what happened at the bottom, is N2O4 giving 2NO2. Okay. So, this reaction exactly takes place as it is written. Okay. One N2O4 molecule at appropriate conditions will split up into 2NO2 molecules without anything else. It will go through a transition state, of course, always it would go through a transition state, but there is no intermediate product, there is no free radicals that are formed in the intermediate step. Okay, that directly goes into this step. Likewise, the other reaction 2NO2 giving N2O4. Okay. If we are only looking at the forward part of the reaction, this is going to be Kc N2O4 and this is going to be, or I will just call it K or K1 K2 NO2 squared. Okay. You would also notice that these do form a reversible pair. So, you will have as a reversible reaction. Okay. And here again our net is going to be K1C the power 2. Okay. Now, what is an elementary reaction? Elementary reaction is reaction mechanism wise reaction proceeds exactly as it is written. Okay. So, because this is an elementary reaction, you may not write this as okay. So, the reaction is elementary, the way you have written it is not in the elementary form, and therefore, this is something that you would therefore want to avoid when it comes to elementary reactions. Okay. Some non-elementary mechanisms or some non-elementary reaction rate. Once I had talked about. So, this particular reaction is very important in case of deposition of what is SB? Antimony, right? Okay. So, it is useful in some kind of a deposition reactions in semiconductor. So, you do have this particular reaction taking place in the gas phase. Okay. That is, it is not an elementary reaction, it does not take place, hydrogen just does not on its own split up and form H2, it undergoes multiple step. Okay. And this is an example of power law kinetics, and this power law kinetics were described in I think 1915, 1918, something like that. Okay. So, this is an example of a non-elementary reaction. Hydrogen plus bromine giving HBr. Okay. This is again an example of a non-elementary reaction. In 1907, this was the first reaction where Bodenstein came up with the mechanism of the reaction and then developed the overall rate law, which looks like this. Okay. So, the mechanism that they came up with is H2 okay. So, this is an initiation step, these are propagation step, this is termination step. This was probably amongst the first reaction where we are using formal tools. People were able to look at the overall reaction rate, which is of this form, and figure out the overall mechanism and then connect the mechanism, the individual rates of these 4 reactions back to the overall reaction rate. This is something that we will do in the class after next. Okay. How do we go from a mechanism to an overall reaction rate? Okay. And we have already talked about Michaelis-Menten and Langmuir-Hinshelwood in the previous lecture, or the one before that. I talked about Michaelis-Menten, where you have enzyme plus substrate forming enzyme substrate complex, and the product being formed and product getting detached from the enzyme. Okay. So, that was how this particular mechanism was developed, and how do we do that? We will come to that in the next module. Okay. So, these are all examples of non-elementary reactions, and over here as well as in the previous lecture, I gave you a brief idea of what we are going to do when we are going to connect reaction rate with mechanism. Okay. So, this is something that in the previous lecture we have discussed. You are all aware of this. The rate of progress of a reaction can be written in terms of a rate constant that depends only on temperature and something that depends only on concentrations. Okay. Now, the Arrhenius law is this part, and you have this T to the power beta term present in an extended Arrhenius form. Okay. Yeah, and if you also bring in the overall expression, then this is what you get. Okay. Likewise, when you have a mechanism like this, your alpha will be dependent on, could be in some cases dependent on the temperature as well. Okay. We will show later on, for example, this KCO is nothing but your equilibrium constant for adsorption of carbon monoxide. This KO2 is equilibrium constant for adsorption of oxygen. Okay. That is something that we will derive next module. Okay. To summarize what we have done, we have defined, we talked about some reaction rate, we talked about the case when a reaction is elementary, how the reaction rates are, and most of these type of reaction rates we were able to capture in this particular slide as well. We also introduced very briefly how a reversible reaction rate of a reversible reaction, net rate of a reversible reaction is going to look like. Okay. And that is the point that we are going to carry across in the rest of this lecture. Okay. We are now going to also start talking about thermodynamics and start relating all of the concepts for reversible reactions to the things that you would have done in your thermodynamics course, or you will be doing in your PG thermodynamics course as well. Okay. Now, before we go to the thermodynamics, we will talk about kinetics. Okay. So, question is, how do you measure reaction rates? How do you think we can measure reaction rates? Okay. Have a reactor, measure concentration, at the exit of reactor. How did you do this in your school chemistry lab? Yeah. Titration? Titration. In school, what we did was, then what did you do? School or maybe your undergraduate chemistry labs. Compute dC by dt from time versus concentration. Okay. So, reactor, if it is continuous reactor, you measure concentration at exit, So, you either run a continuous reactor or you run a batch reactor. Okay. If you run a continuous reactor, you measure the concentration at the exit. Okay. Let us say that you are running a plug flow reactor at steady state. Okay. Reaction, sorry, rate expression for plug flow reactor at steady state okay. So, you run the reaction under conditions in which you can isolate one particular reaction okay. And we will write dfk by dv as when is dfk by dv approximately equal to dv delta fk by delta v? Constant slope or small changes in volume. How do you know that the volume is small enough? Okay. Let us say an explosive reaction where the reaction takes place very quickly, that can literally happen in very small volumes. Okay. There is a concept called millisecond contact time. Okay. So, if you have a reaction like combustion, okay, it takes place in contact time, which is tau of approximately 1 millisecond. Okay, that is why it is carried out in a micro reactor. Okay. You have seen flames, right? Bunsen burner flames. What would happen if you take that burn? I mean, have you seen that experiment when that flame is taken and put inside a tube? Not seen YouTube videos, fun YouTube videos, right? Okay. Okay. So, what would happen under different conditions that the flame will propagate to a particular point and then it will get stabilized at a particular point, and that flame is fairly small. Okay. And if you consider what is actual flow rate versus how small the flame is, keep in mind you have started with a flow rate of 5 liters per minute, temperature has gone from 300 to say 2000 kelvins or maybe 2100 kelvins at the flame. So, the flow rate has increased 7 times, PV equal to nRT, okay, or PQ right. Molar flow rate remains the same, R remains the same, pressure remains the same, temperature remains the same. So, temperature changes. So, what happens? Temperature change is reflected in volumetric flow rate change. So, the volumetric flow rate change has increased almost by an order of magnitude. Okay. So, you have such a fast moving gas and comparatively such a small flame. So, your Q by V, or sorry, your V by Q is really small. Okay. So, coming back to that question. So, therefore, and if it is a very slow reaction, you might take a meter long reactor and still you will get still a constant slope. So, constant slope is really the thing that one wants to look at, but we are doing experiments. So, what else can we look? Yeah. We can have lesser number of points, greater number of points, correct. How can you have greater number of points between inlet and outlet? In between, what else can you do? Okay. So, there are multiple ways, very good answer. There are multiple ways in which you can do that. How do you determine if delta V is small enough? To ensure your delta F is small enough. How is delta F small enough? delta F is nothing but Q multiplied by C. Okay. Let us assume that Q is constant and take Q out of the delta, it is Q multiplied by delta C. So, you ensure that the delta C is small. Other thing that you ensure is basically you run this at say Q equal to 1, run it again at say Q equal to 2. It is usually tougher to change the volume. Okay, but remember what we said, you do not have to look at volume, you can look at tau. So, instead of running the reaction only at Q equal to 1, you will run the reaction at Q equal to 0.5, Q equal to 1, Q equal to 2. If it is truly a plug flow or truly a CSTR, if it is truly ideal or almost an ideal reactor, okay, changing Q from 0.5 to 1 to 2 is equivalent to changing the V from V to V by 2 to V by 4. Okay, because or V to V by 2 to 2V, okay, because it is V by Q that matters. So, you half the Q, it is equivalent to doubling the V, right. So, that is how you run, and if you get basically the slope to be constant, yeah, that is essentially the regime in which you can calculate the rate. But you will not do that because you want to minimize the number of experiments. So, what we usually do is we run experiments where your delta C or the change in or your conversion. So, conversion right. So, we run this reactor where the conversion is of the order of 1 or 2%, okay, and we measure our reaction rate. Okay. What do you do if it is so delta V tends to 0 implies delta F tends to 0, which implies conversion is of the order of 1 to 2%. Okay. This also ensures usually that our that only the main side reactions take place. If it is a parallel reaction, then the parallel reaction take place, but if it is sequence of reaction, then subsequent reactions do not occur. Okay. So, this is if you are doing it in a PFR. Okay. But if you are doing this in a CSTR, what would you do? Now, sorry, not CSTR, a batch reactor. Batch reactor you have right, same concept. Okay. You get multiple points, okay, and calculate the rate as delta nk by delta t. You collect the points close enough in time. Okay. You can do it in two ways. Okay. And at each point you can calculate the rate as the slope using numerical differentiation, okay, or you can only look at these points and use initial rate. Okay. In most modern research, we usually use only the initial rate, because at this point your rate starts getting affected by the products that are being formed. If you have sequential rate of reactions, then the subsequent reactions start playing a role and so on. Okay. So, if you expect the reaction to be A going to B and B plus A, let us say going to C, if your reaction is something like that, you will run the reaction A going to B once, then you will run the reaction by putting A and small amount of B and see the effect of B, okay, so on and so forth. That is how the experiments are usually run. That is where the design of experiments come into picture. Okay. So, let us not worry about that. Let us go back to what we said is, from the experiments we want to obtain the parameters. We will use the design of experiments in order to figure out what are the most relevant conditions to run this reaction, so that what you get is representative of the reaction rate. Okay. Why do I say representative of reaction rate? Because on the right hand side it is not small r, but it is capital R. So, your right hand side, it is basically okay. What we will do experimentally in our lab is, we will do one set of reactions where, let us say we have R1, R2, R3, one set of reactions under conditions where only R1 takes place. You will then repeat the experiments under conditions where it is mostly R2 that is taking place, then repeat it under conditions where it is mostly R3 that is taking place. Okay. So, let us look at, for example, the methanol synthesis example that I took. Okay. What we will do is, we will run the reaction with CO2 and hydrogen at low temperatures and very high pressures. At high pressures, it is methanol reaction that will get speeded up quite a lot. So, we will get an idea about methanol reaction. Then we will repeat it at atmospheric pressure and slightly higher temperatures. So, that is the water gas shift reaction, CO2 plus hydrogen, reverse water gas shift reaction that is promoted. Okay. Then we will repeat the experiment by putting CO and hydrogen. So, that it is CO to methanol that is taking place. Okay. Then to verify all of this, we will repeat the experiment with CO2 plus CO plus hydrogen. Then we suspect that water is, for example, doing a role of an inhibitor, let us say. If we suspect that, then we will run the reaction with CO2 plus hydrogen plus a little bit of water. Okay. If rate of reaction with and without adding the water remains the same, that means water is not an inhibitor. If the rate increases by adding water, water is a promoter. If rate decreases by adding water, water is an inhibitor. Okay. This is how we experimentally run in the lab. So, even if you go to the lab today, one of my students, well, not necessarily today, but maybe in a couple of weeks from now, she will be running experiments on ethane dehydrogenation. Okay. And she will exactly be running the experiments like this. Okay. Run it again and again under different conditions. That is where design of experiments, a course that Professor Kannan teaches, becomes very, very useful in this context. Okay. So, we do not have too much time. So, I will leave you with this. This is what I would want you to do in the rest of the day, is how to use the reaction rate. One thing where we will use the reaction rate is for design of a CSTR of PFR. Okay. This is solved here, okay, and go ahead and read ahead and take a look at how it can be solved. also read ahead with respect to reaction equilibria. Okay. That is what we are going to do in the next class. The class after next is going to be tutorial. We will have problem sheet 2 that we will solve, not tomorrow's class, but day after tomorrow's class. So, the next class we will finish this off. We will also, please pre-read this before coming in for the next 2 classes. Okay, this pre-reading will be useful for your assignment as well. I repeat, assignment has been uploaded. Assignment due date is a week from today.